Okay, so good morning everyone. Let's continue with the discussion on timing analysis. Okay, so yesterday there were a lot of people who were not very clear on why there should be a hold violation. Okay, that diagram probably was not very clear. So I'm going to try and explain it by combining the max delay and the min delay waveforms. Okay, first we will do max delay and then I'll show you what will happen in the next cycle. Okay, so that it becomes very clear. And also what the problem was, we probably didn't draw the timing to scale in terms of the contamination delay and the propagation delay, right? The contamination delay can be very small and propagation delay can be quite large. Because of this you will see a problem, but let's look at it now. Okay, so I have a flop based system like this. I'm going to draw this small. Okay, some combinational block like this, another clock. Right, so this has a delay of TCD, TPD. Okay, so this is D1, Q1, D2 and Q2. Okay, so we'll draw this for across two cycles, fine, and then we'll see what has to happen. So my clock basically goes high here, okay, 5. Then my D1, right, is going to make some change, sorry, here, right. Now I will also do one more thing. I will mark my setup and hold time windows in red. Okay, so you see this is my setup time window. Right, this is my setup and hold time window, right, where data should not change. Similarly, on the next rising edge, you have the same constraint. Okay, this is my setup time and this is my hold time. Okay, so we said now Q1, right, is going to change after the clock, right. So what will happen is you will find that this Q1 starts changing here, makes some transitions, okay, and then goes like this. And it's going to remain like that through the entire period. Okay, D2, what happens to D2? It starts changing after some contamination delay and then settles after the propagation delay again, right. So if you look at this guy, remember this change can happen right here. Okay, let me draw this more or less to scale. Okay, as soon as this Q1 starts changing, there can be a path in the combinational block which will actually race to the output, and therefore you don't have to wait for the propagation delay to finish for the combinational block to start changing, output to start changing. Okay, so therefore the contamination path can start earlier. Okay, and then there is going to be Q2, right. Of course Q2 we don't have to worry, we just have to see when this has to set up. Okay, so what is the max delay constraint? This from the clock is going to take a delay of T what? TPCQ. From this delay, it's going to take a delay of what? This TPD. And at most, right, that change has to happen a setup time before, right? So this edge can technically move all the way to here, right? That's the worst case constraint, right? So therefore we said the max delay constraint is TC should be greater than or equal to TPCQ plus TPD plus T setup. Worst case. Okay, clear? Now you look at D2. Okay, this guy has to hold the data. Okay, let's assume that this data change, this contamination delay went all the way, I mean the propagation delay took it all the way near the setup time. Clock frequency is very high, right? D2 has to hold this data so that Q2 can be sampled correctly, right? So what is the region in which D2 should not change? This window, right? Now once D1 has been sampled, because we have a flop based system there, D1 is free to change at some point. It need not wait till almost the next cycle. It is free to change after what point? After the whole time window, right? So again here D is free to change after this window. It should not change here, that's all, right? Because if it changes in this window, then Q1 will not get sampled correctly. Okay, so let's assume now D1 makes a change like this. Okay, will Q1 get affected? No, because it's a flop, you are past the sampling edge. When will Q1 get affected? In the next cycle, right? So you come all the way here. Let's assume that D1 is, okay, so I am going to call this event 1 and Q1 is now working on event 1, this is working on event 1, okay? Now you look at D1 on the next sampling edge, right? The moment the clock goes high, Q1 will start changing, right? And remember, it need not wait till, right? The moment Q1 starts changing, I told you that D2 also can start changing. So if you look at it, technically, as soon as this thing starts, in fact, it need not even go all the way there. Let's probably cause a violation. Right? D1 has changed as soon as on the next clock edge. So this is sampling event 1. This is sampling event 2. Right? I should use a different color. Maybe what color? Blue. No, dark blue. Event 2. Right? So this has become event 2. Q1, this is event 2. Okay? What has happened now in D2? Will Q2 get sampled to the value of event 1 or event 2 now? Huh? It can be arbitrary, right? Basically, essentially there is a violation because the change in D1 has raced through, right, and contaminated the value that should have been sampled by the next flop. Correct? So that's why this delay, now here if you look at it, this is what? T. What is this delay? TCCQ, contamination clock to Q delay. From here there is another contamination delay on the combinational circuit. So this is TCD, right? And therefore, what is the constraint in which, what is the condition under which this will function correctly? That change in D2 should happen outside that hold time window, right? Which implies the min delay constraint therefore is T hold should be less than or equal to TCCQ plus TCD. Okay. Now we said that okay, there can be skew in this, and by the way, skew is, it's not just the positive edge moves, the entire clock will move. There is a phase shift between these two clocks. Okay, if only one edge randomly moves, which means the time period of that particular thing comes down for that moment, right? Then that's called jitter. That's a random event where one edge can just move like this. Here the whole clock, because of the delay in the clock distribution network, right? Delay difference in the clock distribution network, the whole clock shifts. That is skew. Okay. So now we basically do, come and add the condition of skew. So we say that, okay, this clock edge can move like this. So for the max delay constraint, this is the worst case delay. For max delay, this is for okay, and then you basically go ahead and add the constraint of skew into this equation, plus T skew, right? And this is T skew plus T hold should be less than or equal to this. Okay, is this clear? I hope this has made it clear, right? You had a question yesterday as to what is it that is getting contaminated, right? So hopefully this picture should make it very clear, right? You look at, practice drawing these waveforms one after the other, max delay, and then you look at the min delay, right? Otherwise you do not know what state the earlier thing was in, right? And therefore you are not sure it's actually getting contaminated. That's the problem. Clear? And also mark this hold setup window, because next we'll go to latch, and there it's not the rising edge that is going to become your sampling edge, it's a falling edge. So you have to be very careful. So mark that window very clearly. You should not have a violation in this region. Then it will be very clear as to how to obtain the timing constraints. Okay.